esteemed colleagues and guests, it is my great pleasure to open the third day. We have a very exciting day planned, and before we start this plenary session, I want to highlight that we have 13 technical sessions today and 2 poster sessions during the morning and afternoon breaks. In addition, there will be a lunchtime side event in room M3, and it will be on the IAEA's activities that are related to SMRs. This event will include presentations from various IAEA departments and perspectives from 3 embarking countries. And last, tonight we have a very exciting event, SMRs and microreactors towards a sustainable and equitable future. This is a young generation event, but all are welcome to participate. And it looks like instead of M3, the lunch side event is M1. It's this location right here. Thank you. The event this evening will include a multi-generational, multidisciplinary panel that will delve into the opportunities and challenges posed by SMRs and microreactors. And now to our plenary session. It's on innovative SMRs. As we gather here, we are reminded of the critical role that innovation in nuclear technology plays in addressing the global energy challenges of our time. With the increasing demand for clean, reliable, and sustainable energy, innovative SMRs offer promising solutions. Their flexibility, enhanced safety features, and potential for cost-effective deployment make them a key component to the future energy landscape. The IAEA has been at the forefront of promoting and supporting the development and safe, secure deployment of advanced nuclear technologies. Their commitment to advancing nuclear technologies is crucial in helping countries achieve their energy goals while ensuring safety, security, and sustainability. Today, we are very privileged to have with us a distinguished panel of experts who are at the forefront of innovative SMR research and development. Each of our speakers brings a wealth of knowledge and experience, and I'm confident that their presentations will inspire fruitful discussions and collaborations. Thank you so very much for joining us today, and I look forward to a productive and enlightening session. I will now turn it over to Anna Gomez and Vladimir Kriventsev to begin the panel discussion.
Thank you very much to our conference president for opening our plenary session on innovative SMRs. Good morning, dear colleagues. My name is Anna Gomez, and I work in the IAEA Department of Nuclear Safety and Security, where I am the head of the Safety Assessment Section. And I will be co-moderating this plenary together with my colleague, Vladimir Kriventsev, who works in the Department of Nuclear Energy and is the team leader for fast reactor technology development. Thank you very much for joining us today. We have a very exciting session of just over an hour ahead of us to discuss the latest advancements and future directions in innovative SMR designs. During this section, we will explore the breadth and diversity of innovative SMR concepts and the development globally, and we'll discuss the key challenges and opportunities for innovative SMR deployment. We will also highlight efforts made by regulators to enable the safe and secure deployment of innovative SMRs, and we'll emphasize the importance of international collaboration. I encourage you all to participate in the discussions, ask questions, and share your perspectives. And if you have suggestions for our work on innovative SMRs at the IAEA, we'll be delighted to hear them and take them forward. Now, I pass the floor to my colleague, Vladimir.
Thank you very much, Anna. Thank you for a nice introduction. And it's now my pleasure to introduce our panelists here. Could we see the first slide, please? And first is Dr. Stéphane Sarrat, who joined the French Commissariat of the Energy Atomic, okay, I cannot say it in French, which is we know as a CA in France in 1995. Since 2020, he is the CA Director of Energy Programs Directorate with responsibility for low-carbon energy R&D programs, including nuclear and renewable energy. Since 2023, Dr. Sarat is the Vice-Chair of the Generation for International Forum, and he will be assigned the Chair of the GIF in 2025, correct? So for this, Stefan will provide an overview of the work of the GIF in general. Our next panelist is Dr. Sara Perez-Martin. She is a senior researcher at the Karlsruhe Institute of Technology in Germany, and Sara works in the field of safety assessment of sodium-cooled fast reactors. Dr. Perez will discuss the innovative approaches and safety features of the sodium-cooled fast reactor correspondingly. Another competitor for the sodium fast reactors is the lead-cooled fast reactors, and here today, Dr. Mariano Tarantina, who is the head of the division of the nuclear energy systems at the Italian National Agency for New Technologies, Energy, and Sustainable Economic Development, ENEA, we know these organizations. Dr. Tarantina has more than 20 years of experience in heavy liquid metal technology for nuclear applications, and he will provide an overview of the developments and potential of the lead-cooled nuclear systems. And then Mr. Frederick Reisma, it's here, with a little bit wrong setting, who has a more 25 years experience in high-temperature reactor designs and safety analysis. 13 years he spent on working in the Pebble Bed Modular Reactor project in South Africa, and since June this year, Frederick is the head of nuclear power technology development sections in the area, which I belong to, my boss. So, and our section covers all innovative reactor technology. Frederick will discuss technological aspects and advantages of the high-temperature gas-cooled reactors, all technology, and his presentations with very nice and interesting title, More Than Just Hot Air. It should be helium, I guess. Then we have Professor Jan Lien Klosterman, who works in Technical University of Delft in Netherlands, and he is a full professor of nuclear reactor physics, head of research section of the reactor physics and nuclear materials, and a chair of the Department of Radiation Science and Technology. Professor Klosterman was involved in the molten salt reactor research more than 15 years, and he will, of course, discuss this molten salt reactor technology, and this is benefits and challenges probably, especially in adaptation to SMRs. Last but not least, we have Ms. Sarah Jan Eton, and she is representing the big part of safety, it means from the regulator side, and Sarah is the director of the General of the Directorate of Advanced Reactor Technology at the Canadian Nuclear Safety Commission, where she works since 2009, I believe. And her responsibility is for licensing of new nuclear reactors, pre-licensing activities, including the vendor design review, and leading CNSC SMR readiness project. Sarah will address critical aspects of the safety and regulations for the advanced reactors. Welcome, and please listen to our panelists. Anna?
Thank you very much. So now we start with our first speaker, Stefan Sarat, please. The floor is yours.
Thank you for the
Could we see the next slide, please? My green button doesn't work. Okay.
Seems to work. Thank you very much. Good morning, ladies and gentlemen, distinguished colleagues. It's a pleasure for me this morning to open this presentation. Of course, I'm from CEA, but this morning I will speak on the behalf of the Generation 4 International Forum, and I'm very honored to be the next chair with the incoming years from 25 to 27. So, what is GIF? GIF is more than 20 years in terms of expertise, and it was formed in 2001. And it's a multilateral international collaborative research and development, so focusing on R&D on the Gen 4 nuclear energy system. So we have 8 major technological goals defined for the Gen 4 system in the broad areas of course, sustainability, economics, safety and reliability, and proliferation resistance and physical protection. So GIF identified and focused R&D effort on historically 6 reactor technologies that could meet these goals. Of course, we have gas-cooled fast reactor, GFR, lead-cooled fast reactor, LFR, molten salt reactor, MSR, supercritical water-cooled reactor, SCWR, sodium-cooled fast reactor, SFR, and finally, very high-temperature reactor, VHTR. So GIF's current membership includes 13 countries and Euratom, representing 27 European Union members. And of course, we are dealing with the support of OECD NEA for technical secretariat. So in terms of major goals, of course, we have sustainability, what it means in terms of long-term fuel supply, in terms of minimization of waste and long-term stewardship burden. We focus also on safety and reliability with excellence in safety and reliability, of course, very low likelihood and degree of core damage, eliminate need for off-site emergency response. We also work on economics with life cycle cost advantage over the other energy sources, with financial risk comparable to other energy projects. And then, finally, we also work on proliferation resistance and physical protection in terms of an attractive material diversion pathway and, of course, enhanced physical protection against terrorism. So the key mission for the past 3 years was accelerating the readiness of Gen 4 systems to meet the net zero goals, the 2050 net zero goals. So we strengthen a Gen 4 system feature for combating climate change with flexible operation and non-electric applications, which is an important point we developed. We support transition from R&D to demonstration and deployment in terms of TRL, but also in terms of regulatory readiness and improved economics. We strengthen GIF relevance to industry with industry engagement and close connection with industrial partners in this field. And we also have a senior industry advisory panel. And then we support the Gen 4 talent pipeline. It's very important for us to increase the attractivity of our field to young generation, to young talents, and we support development, demonstration, and deployment of what we can do on this field. In terms of SMR and AMR, I think we are all convinced that there is a great interest on modular reactor worldwide. SMR, AMR, SMR for us is third generation, AMR is for us fourth generation, and they have a great potential from nuclear to X. We'll come back on this definition. And we are pretty convinced that they will be included as a part of the nuclear energy contribution to meet the net zero by 2050, and of course beyond. I'm pretty sure that you know this map, which is a dashboard of NEA showing recently all the projects, roughly 100 different projects in the world dealing with SMR and AMR. And then we are working on this field. We provide a foundation for the advancement of SMR and AMR because we share innovation, we share research in safety and efficiency. We collaborate in an international way, and we have a good vision of how to align long-term sustainability goals. And SMR and Generation 4 reactors share many technological and policy objectives, and GIF is nowadays currently an important platform for the continued development of SMR and AMR beyond electricity. Last week in London, we had the meeting of GIF, and it was my pleasure as a vice chair to present this slide, which is very important, which is a nuclear domino effect of 2024. Perhaps you know that, and it's connected with the GAFAM, Google, Amazon, Facebook, Apple, and Microsoft. And this is the nuclear domino effect, with Amazon starting with buying nuclear power data center from Talent Energy, and Microsoft signing with a Constellation to provide energy through the former reactor from TMI. Then more recently, Google's with a great deal with Kairos Power, and Kairos Power, the first reactors from Kairos Power is the first for 50 years. That is a non-LWR reactor that obtained the clearance for the construction in the US. 50 years, so it's a very important milestone. And more recently, Amazon, that invests more than 500 million euro to X Energy to develop modular reactors. So we have facing a very important momentum. So collaboration are key for the successful development in this area. And of course, we have a great cooperation with IAEA, and the IAEA participation in GIF methodology and working groups is very important for us. GIF IAEA interface meetings to coordinate collaborative efforts. We have a joint workshop on safety and advanced reactors, and we participate to the NC, Nuclear Harmonization and Standardization Innovative. It's very important for us. SIAP is also from GIF is very involved in that field. And for us, NC and Harmonize by Euratom are very important for us. So we also work on OECD and EA with a Committee on Nuclear Regulatory Activities, on safety nuclear installation, and on technical and economical studies on nuclear energy. And more recently, we joined European platforms as SNETP, Sustainable Nuclear Energy Technical Platform, and the recent Industrial Alliance on SMR that was recently created. Thank you very much for your attention.
Thank you very much, Stefan. Really good overview of GIF and what we are dealing with here today. So our next panelist is Sara Perez Martin. Sara, please, the floor is yours.
Okay, thank you very much. Good morning, ladies and gentlemen, and thank you for sure to the organizers of the conference for inviting me to participate in this panel. I will present you some key features and comparative advantages of sodium fast reactors for small modular reactors. So there is quite different topics where sodium performs good in terms of fuel, for instance, because it's under fast spectrum, which is the operation of the sodium fast reactor. So it means that the production of minor actinides, long-term storage, is lower, so it's not needed. It could allow also the fuel cycle to be closed to recycle and transmute. And also for the core layout, it's foreseen to have safety performance. So we know problems or problem issues about reactivity insertion, so we can tackle these problems by doing a special cake shape for the core. So these are key features where we enhance, for instance, the neutron leakage, etc. I don't go in detail, but just to let you know the key features about this. Sodium itself, it has a good qualities for boiling, for instance. It's high enough. There is a quite large margin for boiling, and the operation regime is also high. So this allows also flexibility in the design and operation. Heat transfer as well allows to have compact cores. So this is for the economics also good. And the reactor layout present a variety between loop design or pool, depending on the option. And then, for instance, for the pool option, the pumps are immersed. So it means that no LOCA is possible. It has a large inertia, so it provides additional inherent safety features. For the safety itself, as I mentioned, there are different ways on how to perform these safety measures. Safety measures can be applied to the fuel level by doing different design of the pins, heterogeneous or shorter in the core zone. There are different options. Passive systems are already included because of the natural circulation performance of sodium. The primary loop is under low pressure, so it means we don't have really to tackle that problem in a high pressure. And then the water-sodium interaction, which is also a chemical reaction we try to avoid, can be addressed by inserting a typical intermediate sodium loop in between the primary and the power conversion system. Another key feature to mention is that it has a large operational experience commercially with more than 500 reactor years of experience. It includes also current projects in China, Russia, India, worldwide. So I would like to mention as well this last point, load following. So because of the high temperatures, we are talking about sodium temperatures between 350 and 500. This allows to have an intermediate thermal storage where with an affordable size we can store energy and then be in a load following mode, supporting the grid stability and the load operation. I present in here just an overview of the different safety measures that we have considered in European projects, for instance. How we are targeting the problems and how to solve such problems by inserting different layers in the core, absorbers, or sodium plenum, etc., so that we can do more safe designs. In comparison with other reactors, we will see afterwards other coolants, etc. There are comparative advantages in sodium cooled fast reactor. Fast spectrum, as I mentioned at the beginning, it produces less minor actinides. So compared to thermal spectrum, it has big advantages. For the temperatures, again, we are talking about high temperature coolant, so the thermal cycle is more efficient. Low pressure, it's also a good feature, and then the high extensive experience, not only for commercial, but also for R&D, small facilities. This will allow to make code validation or to improve the simulation of the system. And this can help in the future for designing more innovative. So, as a conclusion, I just wanted to tell you that sodium fast reactor is ready for being as one of the design for the small modular reactor. Even for this medium small size reactor, it has a larger safety performance compared to the biggest one. And then the integration of thermal energy storage is very attractive also for the integration of such systems in the future energy grid. Last point to mention is that for sure we need R&D, collaborative projects, and maybe IAEA is also here as one of the key actors in putting together many research and utilities together for pursuing this. Thank you very much for your attention.
Thank you very much, Sara. Now I'd like to give a word to another expert in liquid metal cooled technology, Dr. Mariana Tarantino from Italy, who will be explaining us what is the benefits of lead and heavy liquid metal coolants for SMRs. Please, Mariana.
Thank you, Vladimir. Good morning, everybody. Thank you for inviting me to present what we are doing on LFR. First of all, I would like to introduce why we are working on lead. This is something that will help the better understanding how our system are moving forward. So, as mentioned before than me from Sarah, with the lead we can provide to work on closing the fuel cycle. So this is increase the sustainability of our nuclear system, and also thanks to the use of lead, we can increase the safety because we have good performances in natural circulation and heat transfer, and we have a very good margin in terms of boiling temperature. So this will allow us to work our system up to atmospheric pressure, so we don't need to pressurize the systems. And also, thanks to the inherent property of lead, we don't need the intermediate loop as in the sodium, because the lead work very well with the air and the water. then led all of us to perform, let's say, operational systems thanks to the good retention of fission product and high capability to shield gamma ray, and also the density could be advantages because this will avoid by, let's say, by design the problem of recriticality in case of a severe accident. Of course, lead has also some drawbacks. First of all, the density. So this will something that we need to face in terms of seismic analysis, for example. So the pool configuration has been chosen for this kind of system. The melting point could be something that we have to face. So for this, we are designing provisional engineering systems for engineering features for reducing taking account the high melting temperature. A problem could be the opacity, because we need to provide NC service inspection in our system. And of course, as you well know, compatibility of structural material is a problem that we are facing in the development of the technology. So the use of this kind of coolant required the development of new technologies, new systems and components. So far, several work has been performed worldwide. First of all, I need to mention the strong activity that we are performing in the frame of the GIF activity. In the GIF, we are able to stay in touch with, let's say, all the players worldwide. So there, Europe is working with Russia, with the US, with Japan, and others, and China, of course. And it's worth to mention that in Russia, for example, Brest reactor is under construction. So the technological readiness level of this technology is large enough for taking it to, for considering the applicability to the market. And as you can see from this slide, many activities are ongoing in Europe in terms of R&D. Many activities have been performed in Italy, in Romania, in Sweden, in Belgium, and in Germany and other countries. So the technological readiness level of this technology is increasing day by day, and the maturity is growing up very quickly. So according to that, there are now industries involved in the, let's say, in the development of this technology for looking forward to support the decarbonization of the energy mix and to support the energy transition by 2050. It's worth to mention the activity that we performed for several years in Europe, involving also Italy for the Alfred reactor, supported by the Falcon Consortium. This is a consortium in which Enea, Rateni Siena, and Ansaldo Nucleare have worked for a while developing the technology, and presently we are working with our colleague from SEK to further focalize the efforts. Recently, Belgium is moving on the design of SMR LFR. This will take the opportunity, will allow us to have the opportunity to focalize the efforts. And so presently we are discussing, let's say, country agreement between, at the level of the country, an agreement between Italy, Romania, and Belgium, starting from the bottom. So first of all, we are putting on the same table the player, looking forward to have a common roadmap for the development of SMR LFR. Another important project to demonstrate the maturity of this technology are the activity performed by the Swedish colleague. There is the project supported by Akalla with the Sealer 55. It's worth to mention that this program is even supported not only by the country but also by the private investors. And the direction that they are looking for is still to have a compact primary system cooled by pure lead, but with a difference in the let's say in the solution for the material. They are developing innovative corrosion tolerant steel, as well as they are developing uranium nitride fuel, very similar to what the people from Russia are doing for Brest, and compared to what people from Alfred reactor or other players are doing for the MOX with the MOX fuel. And the last but not least, it's worth to mention the big effort that is going to perform by Nucleo. This, let's say, we call still a startup, but it's no more a startup. You see, there are involved 850 people on the project. They are investing more than €500 million in the project, with a huge R&D program, even developed this in Italy, in Brasimone, with the design team in Turin, but with the headquarters in France. They are planning not only to build up the reactor, but to build up also the MOX factory, looking forward to close the fuel cycle. And as you can see from this slide, they have in mind a strong R&D roadmap with a lot of facility being constructed in this year, and a very aggressive roadmap in which they are looking for to put let's say, the first kilowatt on the grid by 2033. So this is very challenging, but they are making very tough efforts on this, and this demonstrates how the LFR is ready for the market. So thank you for your attention.
Thank you very much, Mariano. Grazie, Emilia. Now we move from the heavy liquid metals to the light gas reactors, and we'll see benefits, which will be presented by Mr. Frederick Reisma, the head of the Nuclear Power Technology Development Section. Please.
Thank you, Vladimir. So I thought to title more than just hot air. So hopefully I will, in a few next slides, show you that this is not only a promise, but it's been realized today, and but also show the challenges that lies ahead as we want to go to very high temperature gas reactors, and not only high temperature reactors. So what's the reason people are interested in high temperature reactors? I think the increased temperature has been highlighted by many of the speakers for the other technologies. So high temperature gas-cooled reactors with an outlet of 750 and above, of course, get the advantage of good increase in efficiency. If you use a steam generator, and in the future, if you go to a direct gas turbine, of course, it can be substantially better. This is for electricity generation. It's also have a well-established modular high-temperature gas-cooled reactor design philosophy. And if you follow this philosophy, you can realize many of the inherent safety characteristics of the technology. So, I think today all the designers of high-temperature gas-cooled reactors follow this philosophy, and therefore, of course, have to still do all the work and show that this is true, but more or less can claim that the decay removal can be achieved by all natural means, that you have self-limiting power excursions due to a large negative temperature coefficient, and more importantly, very large temperature margins for your fuel. Of course, you have helium that is not reactive and doesn't influence the reactivity. So you can show that you can design a reactor to have no large release, and that all the radioactivity is contained within your coated particle fuel. And therefore, and this has been already, a case has been put to a regulator that the EPZ can be on the site boundary. And that was accepted. Also, you can achieve high burn-up. So I would say typically the minimum is about 80 gigawatt days per ton. But some of the designs aimed, and many fuel tests has been performed up to 200 gigawatt days per ton. It also have a flexible fuel cycle. Many studies has been done with plutonium and thorium, and some of this fuels has been tested in some of the previous test reactors. So the main characteristics important is the coated particle fuel, the helium coolant, the graphite moderator, and the slow transients. And what I showed on the right is the graph show releases from fuel at different temperatures. And basically, the operating temperature of fuel is typically lower than 1,000. Test has been done to 1,600. That show you don't have any additional release in accident conditions. And you'll see the main releases only occur above 1800 degrees. So large margins to inefficient product release coming from the coated particle fuel. So I think my next message, HDR ready for deployment. So several test reactors over the years, experimental reactors, some prototype reactors. There's currently 2 test reactors, one in Japan and the HDR-10 in China, that has gone through many safety tests and safety demonstrations. So there's a long development history of high-temperature gas-cooled reactors. We have the 2 types, the pebble bed that is shown on the right, and the prismatic type or block type shown on the left. They share many of the same characteristics. So the tries of fuel and the slow transients due to a massive amount of graphite. And in Shindo Bay in China, the HDR-PM 200, so 2 units connected to a single power turbine, has been in commercial operation since December 2023. So what is the challenges? So I think typically we required high enrichment for HDRs. I think the minimum is about 8%. Other designs go up to high assay LEU to achieve the very high burn-up as shown. So a closed fuel cycle is also not possible in the thermal spectrum, although there's quite good utilization of plutonium, and it is a quite effective plutonium burner as well. To close the cycle, of course, you need reprocessing, or that's not been demonstrated at large scale, that the fuel can be reprocessed, although there's some good patents and demonstrations done in the past. The reactors, by this design to have these features, have a very low power density, about 30 times lower than a typical light water reactor. So, of course, to achieve then a sizable reactor, you need very big components. So, as shown to the right, the components are really large. I think the cost of the coated particle fuel is also, because it's quite complex, should always be slightly higher than other fuel options. I think the most important characteristics of HDRs are the high temperatures and therefore the process heat applications of this technology. We know that electricity is only responsible for less than 40% of the CO2 emissions, so the other 60% needs to be addressed, and that's where high temperature gas-cooled reactors can make a huge difference with other technologies that also achieve high temperatures. So 50% of user industrial processes require less than 10 megawatt capability, so that also show that SMRs and therefore HDRs, that's all currently SMRs, is a good solution. So the interest, many different designs throughout the world, many projects at different stages of development, some of them already 20 years achieving good manufacturing of fuel, for example. I think more recently we have some of the newcomers, for example, Jimmy, that was successful in getting phase 2 funding from the France 2030 project. We all heard about Hatch that signed up with X Energy to have process heat applications for their facilities, and now the new announcements that we heard about in the introduction. The HDR-PM that performed on this full scale, they performed loss of cooling accident simulation. So really proven that this inherent safety characteristics is not only true for the small test reactors or for the AVR that did this already in the 70s, but also now on the full prototype or demonstration, commercial demonstration, I should say. And also the Shindo HDR-PM in April was connected to a local district heating, so also demonstrating this activity. And in August was announced that a large project with 2 light water reactors and 6 units of HDRs in one plant will be developed for fuel can be reprocessed, although there's some good patent already in the 70s, but also now on the full prototype or demonstration, commercial demonstration, I should say. And Also, the Shindo HDRPM in April was connected to a local district heating, so also demonstrating this activity. And in August was announced that a large project with 2 light water reactors and 6 units of HDRs in one plant will be developed for specifically only steam production for a petrochemical industry in China. So the advantages, I think, is clear. The challenges, this is last slide on gas good fast reactors. That's not my specialty, but just briefly, this is one of the other systems in Generation 4, so that have the advantages of the high coolant, but a fast spectrum, so can close the cycle. But the challenges are that you need active cooling. It requires, therefore, active cooling of the fuel. If you lose your load, for example, of course, the fast neutrons challenges, and with the helium, of course, you get dose effects on your vessel and structure. And it still requires a lot of R&D. Thank you very much.
Thank you very much. Thank you, Frederick. And our next panelist is Professor Jan Lee. Klusterman is going to talk about molten salt reactors. Thank you, Jan.
Thank you very much. Thank you for the possibility to speak here about the MSR. For those of you who don't know how the molten salt reactor works, you have a primary circuit with a fluoride or chloride salt with uranium and thorium dissolved in it, or uranium plutonium or only plutonium, and the heat is extracted via a secondary circuit to the energy conversion system. Because of the high temperature, this can be a Brayton cycle instead of a Rankine. There is a few options only for the molten salt reactor accessible. That is, you can withdraw a little bit of the salt every day, every week, clean it and pass it back to the reactor core. And you can also dump the molten salt in emergency dump tanks, or you can, because of the liquid form of the fuel, you can extract the decay heat with other means. But in any case, because it's liquid, it's easier than in other reactors, we believe. Here you see the reactor core of the molten salt reactor experiment that ran already for 4 years intermittently in the US from 65 to 69. There's not one molten salt reactor. There's a large variety of molten salt reactors. When you dive into the liquid fuel reactor science and technology, you get all different kind of possibilities that you can utilize similar to the large variety of solid fuel reactors that we have. You can have molten salt cooled reactors, molten salt reactors with a thermal spectrum with graphite as moderator or other moderators. You can have fast reactors with fluoride salts, chloride salts, etc. So this gives you a large variety of options. And that's why I also tend to look at the generation 4 reactors in a different way, that you have at the one side solid fuel reactors with a large variety of options of fuels and coolants, and you have molten salt reactors, liquid fuel reactors, with also a similar variety of options. In the last 10 years in the European framework projects, molten salt reactor accessible, that is, you can withdraw a little bit of the salt every day, every week, with fluoride salts, chloride salts, etc. So this gives you a large variety of options. And that's why I also tend to look at the generation 4 reactors in a different way, that you have at the one side solid fuel reactors with a large variety of options of fuels and coolants, and you have molten salt reactors, liquid fuel reactors, with also a similar variety of options. In the last 10 years in the European framework projects, we have worked on a molten salt fast reactor that you see here in the right bottom corner. And of course, of each of these reactors, you can have small modular designs as well. What are now the big themes in a molten salt reactor that we need to address? First of all, there is, of course, a material generation 4 reactors in a different way, that you have at the one side solid fuel reactors with a large variety of options of fuels and coolants, and you have molten salt reactors, liquid fuel reactors, with also a similar variety of options. In the last 10 years in the European framework projects, we have worked on a molten salt fast reactor that you see here in the right bottom corner. And of course, of each of these reactors, you can have small modular designs as well. What are now the big themes in a molten salt reactor that we need to address? First of all, there is of course a material research area to understand the corrosion of materials in contact with salts and how you can avoid this corrosion. So it's at one hand looking at better structural materials, on the other hand also looking at mechanisms to clean the salt and salt, so how to get rid of the gaseous fission products, how to get rid of the noble metals, other lanthanides, for example, in your salt. This all is a chemical processing plant